Okay, so shall we start? So can everyone hear me?
Yes, I can hear you. Yeah.
Okay.
Yes.
Okay. Thank you, guys. Okay, so thank you guys for joining the second season of IEEE ComSoc SPS ISAC webinar series. So we have finished our first season this August, and we're back at this November, and this will be a monthly 2-in-1 seminar. So every month we will invite 2 speakers working in the area of integrated sensing and communication. And today we are very honored and fortunate to have Professor Zhang and Yimin Zhang as our speakers. Okay, so this webinar series is co-organized by ISAC ETI, ISAC TWG, and OTFSC. So before beginning the seminar, I would like to call for papers. These are some of the future workshops and symposium on ISAC related areas. And this is the second actually symposium on joint communications and sensing with a firm deadline of November 26th of this year. And we're also organizing a workshop on ISAC on IEEE WCNC and IEEE ICC of the next year. And okay, so our first speaker will be Professor Zhang. So Zhang is an associate professor at the School of Electrical and Data Engineering and the director of the Radio Sensing and Pattern Analysis Laboratory, University of Technology, Sydney. And he received a bachelor degree from Xi'an Jiaotong University, China, the master degree from Nanjing University of Post and Telecommunications, China, and the PhD degree from the Australian National University. Okay, so Professor Zhang is passionate about research innovation. He's a world-renowned researcher in wireless communications and sensing. Professor Zhang has published more than 210 papers in leading international journals and conference proceedings and holds 6 patents. He has won 5 Best Paper Awards, including Best Paper Award in ICC 2030, and he is a recipient of Cicero Top Award, Cicero Chairman's Medal, and Australian Engineering Innovation Award in 2012. He's serving as an editor of IEEE. Professor Zhang is one of the leading researchers on joint communication and radio radar sensing, JCAS, also known as ISAC, and perceptive mobile networks with the publication of 16 papers in top journals on this area. So Professor Zhang initiated the concept of perceptive mobile network, which is the topic of today's talk, by defining system framework and demonstrating its feasibility in a set of papers back to 2017. So he has been leading 4 industrial projects of applying JCAS technologies in cellular, Wi-Fi, and UAV communication networks. Okay, so our second speaker will be Professor Yimin Zhang, and I will introduce Professor Zhang in the next talk. So before we begin in the talk, I would like to remind you about our Q&A rules. So during the seminar, audiences will be muted during the seminar, and please do not annotate on your screen. So please remember this, do not annotate on your screen because everyone can see it. So please type your questions and send them to the host and co-host, and we will collect questions from both audiences from Zoom and offsite live broadcasting. And during the Q&A, we will choose 3 to 5 questions to ask a speaker. And you will be named and encouraged to ask questions by yourself. Okay, so much for the introduction, and please, thanks and enjoy. Okay, so I'll hand over to Andrew. So Andrew, please go ahead.
Okay. Thank you very much, Professor Liu. Let me share my screen. All right, can you see that?
Yeah, we can.
All right, excellent. Good day, everyone. I'm honored and pleased to have the opportunity to share with you some of our research experience on ISAC technologies, in particular on applying ISAC technology to mobile networks. My talk is mainly based on the survey paper that was recently accepted. And for more mathematical formulations, you can also refer to our overview paper. I will mainly discuss our own work because due to the limited time, and we'll only briefly review the works by other researchers. So I roughly follow the structure for our survey paper. As you know, there are 3 types of joint communication and sensing systems. Since we mainly use the terminology for JCAS in the past instead of ISAC, so I'll still use JCAS in this talk. We know there are 3 types of JCAS systems: radar-centric, communication-centric, and joint design without using underlying system. PMM is one type of communication-centric design. It integrates JCAS in the mobile networks. So in this talk, we will first have a look at the framework for PMN, and then discuss how to evolve the communication-only mobile network to PMM with the integrated communication and sensing capabilities. And we will also have a look at several key research problems and critical technologies, mainly on waveform optimization, sensing parameter estimation, and the resolution of sensing ambiguity due to the clock asynchronism between transmitter and receivers. So these 3 areas are also the areas that we have studied most so far. PMM, so from the concept or the name, it stands for perceptive mobile network, right? So we try to introduce perceptivity capability to the communication-only network. Then we can expect a ubiquitous sensing network on top of the communication. In general, we can achieve the sensing without compromising the communication performance and without requiring significant new investment. So this, in terms of both the potentials and the cost, this network is very attractive. We can realize sensing based on multiple topologies for communication networks. For example, we can realize it based on a standalone base station. We can also realize it based on the what we call CRAN, Cloud Radio Access Network. We know there are uplink and downlink communications in the mobile network. Accordingly, we can define uplink sensing and downlink sensing. And for downlink sensing, we can further divide it into downlink passive sensing and downlink uplink, downlink active sensing and downlink passive sensing. So for downlink passive sensing, we mean the sensing done using the signal from another base station. So for example, if we refer to the CRAN structure, then we use the signal received at the remote radio unit 3 from the signal transmitted from remote radio unit 2, right? And for active sensing, we mean the sensing signal is coming from the same transmitter. So the passive and the active sensing, they are named in a way similar to the passive and active sensing in radar. And for both the standalone base station and the CRAN structure, we can achieve the 3 types of sensings. And these integrations actually can see different advantages and disadvantages. In particular, for downlink sensing, we have the major problem of achieving full duplex, because particularly in the downlink active sensing, the transmitter and receiver for sensing, they are co-located, right? So the reflected sensing signal is overlapped with the transmitted signal in time. So basically this requires 4 duplex capability. And then for downlink downlink passive sensing, the 4 duplex requirement is not essential. We can relax this requirement by using spatial separated transmitter and receiver, particularly falling to the serial structure. And for uplink sensing, the main issue is the clock asynchronism between the transmitter and the receiver, because in general, the mobile units and the base station, they use separate local oscillators. So their clocks have some offset in terms of both the timing and the frequency, carrier frequency. We will discuss the details later. Have had a look at the signal, the system structure. We now have a look at what kind of signals can be used for sensing. And to summarize, basically all the signals, all the communication signals can be used, but different properties of the signal can lead to different sensing performance. For example, if we have regular signals in the time domain, then we can expect good sensing performance, and a lot of sensing algorithms can be applied, in particular for the estimation of the Doppler frequency. And if the signal is regular in frequency domain, then we can expect a good delay estimation. And if the signal's value is known, then excellent. We can directly use a signal for sensing, or we can remove it, right? And correlation and orthogonality, this property is also very important because ideally for sensing, we require especially orthogonal signals. According to the theorem of MIMO radar, orthogonality can lead to extension of a virtual array with a larger aperture. So orthogonality is a desired feature for sensing signals in particular. And we also expect flexibility in the signal structure and the pre-coding so that we can optimize the signal by considering both the communication and the radar performance. So we have quickly discussed the properties that are desired for sensing, and then we can refer to the 5G NR signals, see what kind of signals are good for sensing. So this figure shows the structure for NR new radio, 5G new radio signal. Basically, we have the frame consisted of OFDM symbols, right? Each frame consists of several subframe, and one subframe consists of 14 OFDM symbols. And these resource blocks, they are allocated to different types of signals. Within these signals, their features, their properties are quite different. And we can actually divide these signals into 3 major classes. One class is we call it reference signals. These signals are mainly used for channel estimation. And they have good properties such as they are orthogonal, they are known, and they are generally regular. They have regular comb structure in the frequency domain. So these are all good properties in terms of sensing, but they are generally irregular and could have varying length in the time domain. This is not good for Doppler frequency estimation. And their presence is generally not very frequent. They are users dependent. So their volume, the volume of the signal is not very large. Another class is a synchronization signal. This type of signal, they have the good properties for orthogonality. They are known and they are short, but they are regular in the time domain. So we can expect where they will appear, right? For the reference signals, we cannot expect when they can come. They are irregular in the time domain. So the synchronization signal, they can also be used for sensing, but they have the disadvantage for small volume. They are sparsely distributed in the frequency domain. So that means we probably can only get a small signal to noise ratio when we use the synchronization signal for sensing. And the third type is data payload. Data payload, it's the main signal in each packet, right? But they are unknown, and unknown in the sense of downlink, in the sense of uplink sensing. If it's downlink sensing, it can also be known because the transmitter receiver, they are either co-located or they are connected. One disadvantage of such a signal is they are statistically independent. This can lead to low correlation, but they are not orthogonal at a particular time. So this is something we needed to be careful when we use the data payload for sensing. If the signal is unknown in uplink sensing, demodulating the signal will also introduce some errors. So this is another disadvantage. But they have large volumes. So eventually, we think a data payload would be a very good option for sensing usage. The key issue is how to resolve the disadvantages that we just mentioned. All right, let's have a look at the channel models that can be used to describe the sensing. We have the time domain and the frequency domain channel models here. We can see that they are quite similar to the ones used in millimeter wave research recently, because they are based on the representation for sensing parameters. Right here we have path delay, we have Doppler shift, AOA, AOD, and the amplitude. So these 5 variables, we call them sensing parameters. In terms of here we say sensing is with respect to the localization and speed estimation application. Some sensings, they don't really need these sensing parameters. For example, in the typical Wi-Fi sensings being studied so far, they don't really care too much about these location and speed related sensing parameters. They are more interested in applying the signals directly. So our main focus in this talk is on the sensing parameter estimation. These 2 channel models, as we discussed, they are quite similar to the existing ones in millimeter wave communication in particular, but there are one major difference here. So this is a timing offset term, and this is the frequency offset term. So these 2 terms for communication, they are not a major concern, because carrier frequency offset, they can be estimated quite accurately. And timing offset, they can be absorbed into channel estimation. Right? They don't need to be separated with the path delay. They can be treated as a single parameter and absorbed in channel estimation. But for sensing, we have to deal with these 2 carefully, these 2 variables carefully, because sensing timing offset will cause ranging ambiguity, and frequency offset and timing offset, they are also time variable. They are time varying because of the instability of the local oscillator. So they changes with time. In this case, they will introduce a random phase shift to of them symbols over some interval, over some long time interval.
Sorry, Andrew. Sorry for interrupting, but it seems that we cannot hear your voice. So can you see what happened?
Can you hear now?
Yeah. Now we
Okay,
can hear
sorry.
you.
I accidentally pushed the button
Okay.
on the controller.
Please.
Sorry. Yeah. So this channel model can represent most of the sensing scenarios that we have discussed, and this is a good one if you want to use it in your research. But just note that we actually ignored the phase shift caused by phase shift within a OFDM block due to the Doppler frequency. So that means this model can only be used in slow time varying channels. And for faster time varying, we will discuss a little bit later. There are potentially many applications, in particular in the smart transportation and smart city. Wi-Fi sensing has been widely used for smart home, although PMN can also be used, but maybe Wi-Fi will still be a more popular option. But in larger areas, for example, in smart city, smart transportation, and also environmental sensing, we can see more we will see more popular applications of PMN in the near future. All right, next let's have a look at how we may evolve the current communication-only mobile network to the one with integrated sensing capability. We first have a look at the hardware, the transceiver itself. This figure shows the main modules of a transceiver based on MIMO OFDM. The purple blocks represent those that can be fully shared by communication and sensing. The blue ones are for communication only, and the black one for sensing only, and the red one is for the module that do cooperation between communication and sensing. So as we can see, a majority of the modules can be shared by communication and sensing. That's why it's very attractive to integrate these two systems in terms of the hardware itself. And network-wide, there are some issues we need to take care of. We first have a look at the major difference between radar and comms. So for radar, we can see there are two major types of radar systems. One is continuous, one is pulsed. For continuous wave radar, they can do 4 duplex operation, but this is achieved by using a special transceiver architecture. Essentially, they use the transmitter signal as the input to the local oscillator so that they can apply a band pass filter to completely remove the leakage signal directly from the transmitter, because the bandwidth of the output signal here is related to the reflect distance. The shorter the distance, the smaller the bandwidth or the low frequency of the signal. So using band pass filter, we can achieve 4 duplex transmission in continuous wave radar. And the pulse radar, they use they are half duplex system because they separate the transmission and the receiving in time. But we cannot really use this kind of techniques in communication systems. We know in communication system, transmitter receiver, they are typically separated. They don't have the locked clock in the 2 nodes. And if they use downlink sensing, in particular downlink active sensing, then transmitter receiver, they are co-located. They have the 4 duplex issue. Although 4 duplex communication has been studied, but it's still a long way to go for practical applications. So the the system modification required are mainly mainly used to deal with the two issues we just mentioned, the 4 duplex requirement and the clock asynchronism. We can have both near-term and long-term solutions. Near-term solution, they are suboptimal. Long-term solution would be the 4 duplex one. The short-term or near-term solutions, we can have a couple of options. For example, we can use a dedicated transmitter, or we use a dedicated receiver. So in this case, we can avoid the 4 duplex requirement. And if we use such transmitter receivers in the serial architecture, their clocks are also locked. So we don't have the clock asynchronism problem as well. These are the potential suboptimal near-term solutions. Yeah, we think there are two near-term solutions that are particularly attractive. One option is for uplink sensing. We don't really need to have clock locked between the transmitter and receiver. We can use signal processing to resolve this clock asynchronism issue. We will discuss more details shortly. And another option is using one specially widely separated receiver antennas for sensing. So we still have the normal transmitter and a normal communication node. We only needed to add one additional antenna. This is separated, especially widely separated from the existing antennas. Since we only require one additional antenna, so the cost will be quite low, and we can use multiple transmitter, one dedicated antenna for receiver to achieve the sensing function. Because in the active downlink sensing case, the AOD can be used as AOA to locate the object. And other estimations, we can achieve similar performance, only some degradation in terms of the SNR. So this would be an attractive option for downlink active sensing. All right, next let's have a look at some key research problems and critical technologies. Because this is a relatively new area, so there are many research opportunities. We have reviewed many of these research opportunities in the survey paper, and due to the time limit, we can only cover 3 here. So we will mainly discuss joint waveform design, sensing parameter estimation, and the resolution of the timing ambiguity. Joint waveform optimization, this is probably the topic that has been mostly studied in JCAS so far. We have seen many optimization ideas. For example, we can optimize the preamble by designing the training sequence. We can also optimize the data payload together with the preamble by considering their, for example, power allocation and the special precoder design. We can also optimize the length of the packets or the interval between the packets so that we can achieve excellent or improved Doppler shift estimation. And we can also achieve in other domains. So we will mainly have a look at the optimization techniques in the spatial domain today. Before we are able to do the joint waveform design, we need to understand the performance metrics for radar and communications. So for radar, we mainly care about, for example, the detection probability. And in terms of the sensing parameter estimation, we're probably mainly interested in the parameter row bound. We also see some work on optimizing the mutual information. And in radar community, the ambiguity function is also an important one. For communications, we care about beta error rate, signal to noise ratio, and capacity and the rate, etc. There are, in our opinion, there are typically two types of optimization approaches when we talk about spatial domain optimization. So one is we use a single precoder, spatial precoder. We can formulate an objective function, lambda p, and subject to some constraints. Another way is what we call the decomposed approach. So here P is decomposed into some submetrics. For example, we can predefine some metrics, some submetrics for communication and sensing respectively. And then we try to optimize the way of combining them to get the P. One example is, okay, P is equal to a linear combination of PC and PS. Then we try to optimize the alpha, the combining coefficient here. They can also be formed as submetrics for the P. And we can also optimize some weighting factors when we, in the way of forming P. We will have a look at a multi-beam design approach to understand the two approaches in more detail. So this is some of our work done back to probably 2018. This is about designing a multi-beam scheme to support different communication and sensing directions for a single analog array. Because sometimes we know, sometimes communication is fixed in a particular direction, but sensing we may want to look at different directions, right? So we need to support the different direction requirements at the same time. And what we do is, okay, we fix the sensing direction within one packet period, and we make it varying for sensing over different packets, but for communication, we make it still fixed. So that means we will need a multi-beam, a beam with multiple sub-beams pointing at different directions. To achieve this, we formulated a combined sub-precoder form, because we only have analog array here, right? So we have the beamforming vector instead of precoding matrix here. Here we have omega TF for the communication function, and TS for the sensing function. We combine them using the parameters rho and phi. So rho controls how the power is distributed, and phi determines how the phase of these two are combined. And based on this expression, we can formulate quite a different optimization problems. But before we can do that, we need to first generate some basic beamforming vectors for communication sub-beam and sensing sub-beam. We applied, developed some technique based on the iterative least square algorithm, so that we can generate any shape that we want with a different, for example, with a different beam width, different side lobes, etc., based on for a single analog antenna array. And once this basic beamforming vector is generated, then we can apply a phase shifting sequence to the basic one to generate a beam pointing at different directions. Then the left issue is just, okay, how to optimize the two parameters rho and phi. We can formulate different optimization problems. So for example, we can formulate one based on the sensing constraint. We try to optimize we try to maximize the received signal to noise ratio for communication while subject to the constraint for the beamforming gain at particular directions for sensing. We can now also formulate one under the communication constraints, right? These are just some optimization games. And come back to the first approach of spatial optimization, right? We optimize a single P instead of for the decomposed ones. Then in this case, we can formulate a problem of what we call the global optimization problem. Here we try to maximize the receiver signal to noise ratio subject to the sensing requirements constraints. Because in the global optimization approach, usually it's quite difficult to get closed form solutions. And solving this optimization problem, it's also complicated. So this kind of global optimization, we think they are generally not very suitable for real-time implementation, but they can be used as a benchmark for comparing how the suboptimal decomposed approach works. For the particular problem we studied, we compared the approaches between the global optimization and the suboptimal decomposed ones. And we found their performance actually quite close. But the complexity of implementation is, in terms of complexity, the decomposed one is much lower. For spatial precode optimization, in addition to those based on the beamforming gain, as we just described, there are also some works based on maximizing the mutual information or minimize the CILB. For mutual information of radar, it mainly represents how good the channel information is contained in the received signal. This is useful when we try to maximize the MI so that we can achieve the optimal pattern recognition performance. Because if we maximize the information contained in the received signal, then we can achieve, we can expect the optimal performance in terms of, for example, object recognition, etc. But they are not necessarily optimal for sensing parameter estimation. So we developed some optimization approaches based on the combined or weighted mutual information for communication and radar. And then we optimized the power allocation between the preamble and the data payload part. Optimization based on CILB has also been studied. But the main issue with this approach is generally it's quite hard to get closed form expression for CILB, mainly because the complicated communication signals in modern mobile networks, because we need to compute the CILB with respect to the sensing parameters, right? Delay, AOA, Doppler shift, etc. Since it's quite hard to get a closed form, so it's quite hard to use the CILB to get some closed form solution for the optimized signal. There are a few works, including our own and Professor Liu's recent ones. In our own work here, we not only studied the CILB-based optimization, we also put mutual information-based ones together, and we compared these two approaches, their performance, their relationship, for example, in terms of the achieved sensing performance, whether optimization based on MI is better than CILB, or whether optimizing one can lead the optimal or nearly optimal output for the other one as well. Our solution finds some loose connections between these two. And in particular, if we optimize with respect to MI, generally we can also expect smaller CILB, but it's not in the other way, which means if we minimize CILB and get the waveform, this does not guarantee we can achieve a good MI. We're not very sure about the reason at this stage. There are also some other works, particular Professor Liu, he has some very well-known work in this area based on the waveform similarity. Due to the time limit, I won't go to the details. In addition to the optimization in the spatial domain, we can also optimize in other domains, as we briefly mentioned earlier. Okay, next let's have a look at the sensing parameter estimation issue. So this is a received signal as we described it, right? We have the transmitted signal, we have the channel decomposed into several matrices. And to do sensing parameter estimation, we think there are two approaches. One approach is we first remove the transmitted signal and separate the channel for different users. This approach, we call it as indirect sensing. And the other approach is called direct sensing. So we don't really separate the channels for different users or remove the received signal. And these two approaches, they have respective advantages and disadvantages. The good part for direct sensing is because we don't remove anything, right? So there will be no distortions or signal errors introduced. We can directly use the signal and formulate the estimation problem. But because the signal is it may be quite complicated, so the applicable sensing algorithm is quite limited. In one paper earlier, we proposed the approach based on block compressive sensing for this type of direct sensing. And to be able to apply indirect sensing, we needed to be able to, for example, remove the transmitted signals, right? In this case, we can see we needed to have a matrix inversion operation with respect to the transmitted signal. So to make this approach work, we first needed to make sure this matrix is invertible. And this means we need to receive sufficient signals. And this reversion will also introduce some errors, because this is similar to what we know as zero forcing equalization. It's just we try to remove a channel, and here we try to remove the transmitted signals. But the effect will be similar. If this matrix is near singular, then we will have very large noise enhancement problem. So this is the potential issue with the indirect sensing. And because of this operation, we say, okay, if this transmitted signal, they are orthogonal, then it will not introduce noise enhancement, and the operation of matrix inversion is quite simple, right? So this would be a good approach if we have orthogonal signals. For example, we have orthogonal channel training sequence. But for data symbols, this may not be a very good option. All right, referring to the case of indirect sensing, we can actually get a clear channel for each user, and we can formulate the channel in this form. And this is a well-known expression in the signal processing domain. It's known as 4D harmonic retrieval problem. We have 4D signals. And there are many approaches can be potentially applied. For example, the simplest one is based on the multi-dimensional FFT. And the next one may be on-grid compressive sensing. We have done quite a lot of work on the on-grid compressive sensing algorithm for sensing in PMA network. And then the performance looks quite good. And more importantly, this type of algorithm, they do not require regular signal. So they can deal with the complicated resource allocation resulted signal structure. In this sense, we think this is a very good option for sensing. And there are also other approaches. We can see they have disadvantages in terms of complexity or the sensing performance. There's no very good trade-off between these two. Subspace methods include traditional techniques, for example, music and Esprit. Esprit also does not require regular signals. Oh, sorry, music also does not require regular signals. So they are also a good option. Music is also a good option for sensing in PMM. Here is a simple result demonstrating the potentials of these algorithms. So this is the period diagram result. We can see the Doppler estimation is quite rough, and the resolution in terms of the speed is quite low. But if we look at the result obtained from the 2D compressive sensing and even 1D compressive sensing, we can see the results are quite good. The red circles are for the true ground truth, and the blue star, they are for the estimates. I also touch briefly on the OTA phase solution. OTA phase is a good modulation schemes or signaling schemes for joint communication and sensing system, because it modulates the signal in the delay Doppler domain, which has good match with the delay and Doppler parameters that we want to estimate in sensing. But one major issue with OTA phase is generally their resolution is quite limited because they are on-grid system. They modulate data symbols in grid or quantized delay and Doppler values. So if we estimate directly these channels in the delay Doppler domain, then we can only get a very coarse resolution. So the major challenge in OTA phase JCAS is how to get fine resolution estimations using the signal structure. Okay, the resolution of sensing ambiguity, this is a very important problem because if we can come out with some good solutions, then we can enable uplink sensing without incurring any major cost, without requiring modifying the network. So here shows one example how the timing offset will impact the sensing, right? We have the propagation delay, but we also have the timing offset caused by the clock asynchronism between these two nodes. So for communication, they are treated as a single one, but for sensing, the timing offset will introduce the ranging ambiguity. So we have to resolve this issue. And there are some existing solutions. We may be able to divide them into network-based and single node ones. Network-based ones, we can use, for example, the triangulation method in localization to remove the timing offset. But this approach, they cannot remove the random phase shift associated with, for example, each packet. And for single node, we can exploit the fact that the offsets between different antennas, receiver antennas, they are the same. So if we compute the conjugate cross correlation between antennas, or we compute the ratio between multiple antennas, then we can get rid of these offsets. Right? So this is the basic fact exploited in most of the current single node based resolution, the sensing ambiguity resolution algorithms. We will quickly have a look at a few. So this is the basic receiver signal, and this is a cross correlation. Right? So we can see the timing offsets and the frequency offsets, they are removed in the output of the cross correlation. But the issue is they introduce doubled terms because we have two L terms here, and all the delay and Doppler shift, they become relative measurements because they are with respect to the reference antenna. So we need to resolve this issue in the cross antenna cross correlation approach. Existing one mainly based on the one called add and minus, which adds one signal to the reference signal from antenna, signal from the reference antenna, and minus one constant in the other antenna. Then in this case, they many of the work show that quite often they can remove the image component, but we found that this doesn't always work well. So instead of using the add minus before the CA cross antenna cross correlation, we actually developed a new technique called a mirrored music algorithm. Because the component as we see here, they are mirrored, right? Because if we use AOM and AOM0 with different values, we will see mirrored components for delay and Doppler shift. So instead of only use the existing music algorithm directly, we actually define the basis vector in the music algorithm in the mirrored form. In this case, we can reduce the unknown parameter from 2L back to L. And we can also resolve the ambiguity due to the imaginary components here. We also developed another technique to resolve the timing ambiguity issue. This is based on the idea of exploiting the line of sight path components. Because the current technique mainly they remove loss components and then deal with the byproduct components. But we found if we exploit the line of sight components, we actually can construct a metric which does not have the image components. And in this way, we can obtain accurate Doppler estimates. And after obtaining the Doppler estimates, then we can construct a metric for AOA and delay estimation. So we have developed a real-time demonstrator based on this approach, which can do real-time single object tracking. We have the tracking videos available from my home page. All right, the last solution I would like to mention is the work from Professor Daqing Zhang from Beijing University. They have done a lot of work based on the CSI ratio, which is the ratio between the signal from two antennas. So they can represent the ratio as this form, where the change of distance is only contained in here. And they show a good relationship, a beautiful relationship between the change of this distance and the CSI ratio. And they can estimate in which direction the distance is changing, whether it's increasing or it's reducing. They have applied this approach to breath detection and show very good results. They claim that this approach can achieve much higher SINR compared to the conjugate multiplication approach before, but I haven't seen a strict proof for this claim. So maybe this is remaining as an open problem. All right, this comes to the conclusion. We have shown that PMN is a very promising solution. It can achieve downlink and uplink sensing, or matching with uplink and downlink communication. And we expect it to deliver a revolutionarily unique sensing solution without compromising the communication performance. Of course, there are a lot of challenges ahead, and let's try our best to make it happen as soon as possible. Thank you very much.
Okay, so thanks, Andrew, for the wonderful talk. And we have received a number of questions, but since we only have limited time, so we'll just name one person to ask his or her question. So Stephen Schiller. So please, Stephen, can you ask your question?
Hi. Can you hear me?
Yeah.
Yeah. Okay. Great. So My first question is regarding the direct parameter estimation. That is, how would you, for example, I'm picturing a scenario with, in the uplink, for example, with the Yimin, one base station. Then how would you perform direct sensing there? Because I imagine that would be different channels, and different channels would be, of course, composed of different parameters. So if you were to do the sensing there.
Sorry, your voice is not very reliable. I cannot hear it very clearly.
So maybe I can repeat Stefan's question. So he's asking how would one perform the task of direct parameter estimation when the received signal is composed of different channels. So how can we estimate parameters of these channels in a joint fashion?
We use the approach called block compressive sensing, and we formulate the signal in the channel together with the signal, transmitted signal in this form, and then we can treat them as a dictionary in the compressive sensing. Yeah, so this can include all the signals and channels coming from different users. So this is a basic signal formulation.
But that would mean you still estimate the parameters of the different channels individually, right?
No, we estimate them together.
But okay, you estimate them together, but they are different parameters for each channel, right?
They can be different, or they can represent the common reflection.
Okay.
Yeah, because some users, they may share some channel, or at least reflection may come from the same object, etc. So there are some.
Okay, but how do you do the matching? I mean, how would you know that the objects are the same?
There are signals. There are signals we'll be able to separate them directly because we have the signals from the different transmitters here.
Okay. I guess I have to read up on it in the paper. That seems like.
Yeah, so there's no matching problem here because we use the transmitted signal directly.
Okay, and maybe just another quick question. I hope my voice is okay now. What do you mean by tensor-based methods for parameter estimation? I think that was 2 slides later. Yeah, tensor-based ones.
This one.
Chronicle plus compressive sensing. Okay, that is tensor-based then.
This is not a tensor-based ones. This is just a 2D compressive sensing.
Okay, but I was just wondering, what do you mean by tensor-based methods? Like,
if we apply tensor-based methods, then we can do the sensing directly in high dimension for high dimension signals.
Yeah, sure, but you don't have like a concrete algorithm in mind when you for the example.
We also tried some tensor-based techniques, but because the complexity is quite high, so when we assess the performance and the complexity, we think 2D ones are better options.
Yeah, I think the interesting part about the tensor-based methods is that you don't have like a matching problem with the parameters afterwards. Right?
Yeah, in this 2D approach, because we only interested in estimate 3 parameters, the delay, Doppler, and AOA, so we can directly estimate the third one, right? 2D can only directly estimate 2, but we can use the estimated results to get the third one directly. So there's no matching problem as well here.
Yeah, okay, thanks.
Yeah, thanks.
Okay, so thanks, Stefan. So maybe we still have 1 minute, so maybe I will have a quick question, I think. So Andrew, you are talking about using pilot and a data payload to do sensing. So we know if you are going to do, for example, uplink sensing, And if you want to exploit the data payload, then maybe we need to do some strategy like sensing after decoding, right? So after decoding the data. So my question is, so I think there are some scenarios for this. For example, if it's the low SNR, then the data cannot be, decoded, at high accuracy. So maybe that is not helpful for sensing. And in high SNR, if you have already very high SNR at the pilot, maybe the data payload will only give you marginal improvements in the sensing accuracy. So in that case, what do you think about which scenario will be suitable for this strategy, sensing after decoding?
Yeah, that's a very, very good question, and you have very good points here as well. I think using data payload cannot only introduce benefits in terms of the signal to noise ratio. Of course, it can increase the signal power and then increase the SNR. It can also avoid some issues maybe related to the resolution ambiguity, because if the interval between the samples are too large, we may not be able to estimate some, for example, small Doppler shift. But if we use the whole packet, then we can actually improve the resolution. This is one benefit, additional benefit in terms of the SNR. And in terms of the application of the data payload at a low SNR case, we may be able to incorporate decoding in the loop, because using decoding, we can largely minimize or reduce the demodulation bit error or the error bit error rate. And also recall that the error generally may be only like 1% at the most if for communication, right? 1% error may be a bigger issue for communication, but for sensing, it's only introducing like 1% error in terms of the signal. So I think the BER error in communication and the error in terms of sensing is quite different.
Yeah, that's a very good point. Yeah.
Thanks.
Okay. Thank you very much, Andrew. So I think I'll begin to introduce the next speaker. So thanks again, Andrew, and you can stop sharing your screen.
Yeah, thank you very much. Thank you all for the audience for your participation.
Okay. And so our next speaker will be Professor Yimin Daniel Zhang. So Yimin Daniel Zhang is an associate professor at the Department of Electrical and Computer Engineering, Temple University. So he graduated from Xidian University, China, and received his PhD from the University of Tsukuba, Japan. His research interests lie in the areas of statistical signal processing and reprocessing, information theory, machine learning, compressive sensing, convex optimization, and time frequency analysis with applications in radar, communication, satellites. And he's an associate editor of IEEE TAES and for Elsevier signal processing, and served as an associate editor for IEEE TSP. He's a member of the Signal Processing Theory and Methods Technical Committee, and was a member of the Sensor Area and Multi-Channel Signal Processing Technical Committee. So he received the 2017 IEEE AESS Harry Rowe Mimno Award for article signaling strategy for dual function radar communication, an overview. So this is a very famous paper in our area. And his publications on sparse array design and sparsity-based DOA estimation received the 2018 IEEE Signal Processing Society Young Author Best Paper Award, and the 2019 IET Communications Premium Award, and the 2021 EuroSIP Best Paper Award for signal processing. And he is a fellow of IEEE and a fellow of SPIE. So Professor Zhang, I will hand over to you, and please go ahead. Hello?
Yes. Okay. Can you see my screen?
Yes, we can.
I think I have a little bit here, right? Okay. So thank you very much, Fan, for your kind of introduction. And good evening, good morning, good afternoon, everyone. So the title of my presentation is Signaling Strategies and Array Processing for Sensing and Communications. So I will break down my talk into 3 parts. The first one is joint radar communications. I'm going to focus on signaling strategies, And then the second part is radar communication coexistence, and my focus will be robust beamforming and the direction of arrival estimation. And the third part, time permitting, I will talk about passive radar. My focus will be sparsity-based imaging, localization, and space-time adaptive processing. So as everyone knows, radio frequency spectrum is a finite resource to be shared by a number of applications. And the explosive growth in wireless communications and other applications result in soared demand for wireless broadband, making spectrum increasingly congested. So spectrum sharing among disparate wireless systems is a solution to this problem. And the particular interest would be between radar and communication systems because of their heavy use. So many different ways can be considered for spectrum sharing. For example, joint radar communications that can be divided into radar-centric and communication-centric. And the coexistence, so in this case, radar and communication subsystems would transmit respective waveforms, and also passive radar. In this case, radar will use the signals of opportunity and for which it does not have a control. Okay, so in the first part, I'm going to talk about the joint radar communications. So in this case, the transmitter system is shared by radar and communication functions. So the apparent advantages include the effective use of the signal spectrum and the hardware. And also, it generates no or minimum mutual interference because the same transmitter system is shared. And the joint radar communication systems can be communication-centric. So in this case, we achieve the radar sensing function in a primary communication system. A good example would be automotive radar that use the IEEE 802.11 family signals designed for wireless network and use them for sensing purposes. And we can also consider radar-centric case. So in this case, the communication information is embedded to a primary radar system, and that will be the focus of my first part of the material. So before I talk about information embedding, I would briefly introduce how radar works. So a typical pulse radar would periodically transmit the same probing waveform, and excuse me, a commonly used waveform is the linear FM waveform. So we can see here, we can transmit these waveforms and periodically, and for each waveform, when the waveform hit a target, then we are going to receive the return signal. And so we sample the signal in the so-called fast time, and then we can perform matched filtering, or in the later terminology, we also say it's a pulse compression. So as a result, the linear FM signal will be returned to a narrow pulse. So in this way, we can detect where the target is in terms of we can get the range information of the target. And then after that, we do the Fourier transform over the signal we received corresponding to different pulses. And then we can get the Doppler information. So for example, in this so-called range Doppler map, we can see there are 2 targets, and we can identify their range and also their Doppler frequency. So in other words, in radar application, we have different dimensions of the signals we can use. So apparently we have the fast time and also the slow time and also the spatial domain when we use an array. So what domain we can use and how we can embed the information really depends on the whole different complexity, but also how much the radar would be flexibly accept this kind of changes. So for example, when we consider in the fast time, the traditional radar systems use the linear FM signal. And then we can modify this to use the coded sparse frequency, or in other words, we can also call that as frequency hopping. So by changing the hopping pattern, we can embed the information. We can also use the OFDM that's popularly used in both communications and the radar. So OFDM signal can carry different informations. We can also consider phase modulation continuous waveform to carry information in each symbol. So the factors you need to consider in embedding information in a radar system, we need to consider several factors. So for example, we need to consider whether the convolution between the transmitted waveform and the receiver filter would maintain identical for each pulses. Or whether you would accept a wideband IF signal after demodulation or match the filtering. Or whether you can accept a high peak to average power ratio. Or what kind of ambiguity function you would accept. So we can also consider information embedding in slow time. And for example, in this very old paper published half century ago, uses on-off of several slow time pulses. And then with that pattern, you can carry information. You can change the phase of these pulses to carry information. We can also carry information in the spatial domain, for example, by changing the side lobe levels and by changing the phase, and also you can use the index modulation by turning off some of the antennas. So we mainly focus on the spatial domain signaling that does not require major changes to the radar signal waveforms and the receive structure. So we are going to consider to maintain the radar main beam patterns. We are not going to change the main beam patterns, but we are going to carry the information in the side lobe region and also or in the signal phase. So let's consider a very simple case, and we have a single communication user, and at the direction of theta c, and that lies in the side lobe region of the radar operation, and the steering vector is a theta c. Okay, so we can design two beam forming vectors, W1 and W2, and such that when you use W1, the array gain towards the direction of the communication signal is delta H, it's a high level, and whereas if you use a W2, the level will be lower. So by using this high-low, you can embed the information toward the direction of the communication signals. So for example, we can design W1 using this optimization-based design to make sure that the array gain in the radar region, main lobe region, would remain the same as desired. This GD theta, right? That's the desired beam pattern. Whereas in the side lobe regions, the array gain would be below a certain threshold. And then we can design for the specific direction of the communication direction that will get this delta H. And also we can similarly design W2 such that these conditions are the same, but this one will be delta L. Okay, so in this way, we can see here for this example, the delta H is minus 20 dB and my delta L is minus 50 dB. So by switching between W1 and the W2, the radar function is not affected because both of them provide the same main beam pattern, whereas the side lobe levels are changed. So the communication user can detect whether this is a high and low. By doing this, we can embed the information. Okay, so the output, the transmitted signal will be either this term or this term, and the B is the information bit binary number 0 or 1 to control this. And we can also design multiple orthogonal waveforms, and such that independent information can be carried in each of these subcarriers to carry more information. So when we look at this kind of scheme, we can design them to support multiple communication users. For example, in this example, we have 3 communication users in the direction of -50°, -30°, and 40°. So in all these directions, we achieve very low BER. Whereas we see that the BER at other directions are very high, that means this system is secure against eavesdropping in other directions. Okay, so when we look at this kind of a scheme, one problem definitely is this is only for side lobe communication. So we cannot communicate in the main lobe of the radar operation. And also it will be sensitive to channel fading because we are using the amplitude. So we can also consider phase-based information embedding, and so we can carry the information in the phase of the waveform. So in this case, we can deliver information to both the main lobe beam and also the side lobe regions of the radar operation. And it's less sensitive to the channel fading, or say the magnitude variation of the channel. So one thing we need to consider in this case is that if you only consider one pulse, and then you have to carry on a reference phase information so that the receiver can understand what's the phase, because if you just send a pulse, the receiver just cannot understand what's the phase because there is no phase reference. So one way we can do is that you can send out this information to carry the information, and also you can send another waveform at the same time. They are orthogonal, and you can carry this term will carry the reference phase information, so you can understand what the information is carried here. And apparently we can also modify this kind of work to higher constellation. For example, we can use the QAM modulation, and in this case, the information can be carried in both the amplitude and also the phase. And we can also design the beam pattern such that the different magnitude or phase will be delivered to different users. So definitely in this case, we need to design a high number of waveforms, or say the beam, beam forming weights. So to support the C communication users with a form of L amplitude levels and Q distinct phases, we needed to generate N equals to LQ of power C beam forming vectors. And then in this case, in total, we can carry C of log 2 LQ bit per pulse. Okay, and we can also, if the array is large, we can also consider antenna selection to reduce the number of our RF chains. So one way we can do is we keep all these kind of requirements in terms of the main beam, and in terms of the side lobe, and in terms of these information. And but at the same time, we can minimize the total power and also the sparsity, or say the group sparsity of the weights, because we are designing many different beamforming weights, right? So for example, if we have beamform 1, beamform 2, so in this case, we jointly design their sparsity so such that this antenna and these 2 antennas can be turned off. So to have a quick remarks on the first part, joint radar communications, and we consider the information embedding in radar-centric systems. And in general, radar-centric information embedding can use the fast time, slow time, and spatial domain resources in the radar system. We mainly focused on the spatial domain information embedding because that requires minimum modification to the existing radar operations and radar systems. However, other forms of information embedding are possible as radar systems become more flexible in accepting different operation modes and the system configurations. Okay, so the second part, I will talk about radar communication coexistence. And coexistence of radar and communication systems would permit more flexible operations. So one problem is that mutual interference would exist between radar and communication systems because they are transmitting their own respective waveforms. So it is important to perform robust beamforming to mitigate mutual interference. So we consider a very general and simple receive array signal model. So in this case, we have XT, we have the design signal component and interference component and the noise component. So apparently when you design a beamformer, the goal is to get the output of YT, and then that should be as close as possible to the desired signal. So a really effective beamformer is the NVDR that minimizes the interference plus noise power while keeping the desired signal unaffected. So we can see here it's trying to minimize this, and this represents the power of the interference plus noise, and this RG plus N is the interference plus noise coherence matrix. And then the constraint is that the array response in the direction of the desired signal is 1. That means that the desired signal is unaffected. And this solution is well known to be given by in this expression. So this is an inversion of the interference plus noise coherence matrix and multiplied by the steering vector of the desired signal. In practice, people may feel the estimation of the interference plus noise coherence matrix is difficult. So in this case, we can replace this with the data coherence matrix. And then in this case, we call that as the MPDR because it will minimize the output the power instead of the output interference plus noise power. And we still have the same constraint, and the solution is given by a very similar format, but this term is replaced by the inverse of the coherence matrix. So MPDR is commonly used because it's easier to implement and is equivalent to NVDR in the statistical sense when we have the accurate estimation of the coherence matrix and also the steering vector of the desired signal. However, MPDR is not robust and its performance degrades when the estimated coherence matrix RXX hat is inaccurate. For example, because of insufficient data snapshots. Or the presumed desired signal, the steering vector is inaccurate, maybe due to imperfect estimation, or maybe due to the multipass feeding or calibration errors. So in this case, there are a number of robust beamforming techniques being developed by looking at the coherence matrix and also the steering vector. So for example, the diagonal loading approach look at the coherence matrix by adding a diagonal term to make the beamform more robust. And whereas the worst case beamforming look at the steering vector, so it still minimizes the total power outputs, but instead of constraint in the direction of the desired signal, because this steering vector may have errors, so it constrains such that around the steering vector, the output, or say the array gain would be at least 1. So in this case, signals around the presumed steering vector will not be suppressed. So we propose a robust adaptive beamforming based on the reconstruction of the interference plus noise coherence matrix. So the idea is to estimate the DOA and the power information of each signal, and then we reconstruct the interference plus noise coherence matrix based on the estimated power information and also the steering vector in this way. And so in this way, we can exclude the contribution of the desired signal, and by either excluding that component, or if you know the region of the desired signal, you can also exclude in these components. So in this way, we can reconstruct the interference plus noise coherence matrix to perform robust beamforming. So we can show some simple examples. So here we have a 10 sensor uniform linear array with one desired signal, and the presumed direction is 5 degrees, and we also have two interferers from -50 degrees and -20 degrees, and we only use 30 snapshots. So we can see here for the first example, the direction of the desired signal actually has a certain uncertainty and up to 4 degrees. And so the actual desired signal will come from any point between 1 degree and 9 degrees. So in this case, we can see that many methods, including these diagonal loading, this one here, and also the worst case here, actually they do not provide a good performance, and as the input SNR increases, whereas our method provides the performance very close to the optimum case. We can also look at the case when the desired signal has coherent or incoherent local scattering, means that the desired signal is corrupted by multipass, and we can still get very really good results. Okay, that's close to the optimum output signal to interference plus noise ratio. Okay, and we also, if the steering vector has a mismatch, we can also estimate the true steering vector by minimizing this result. So this result, we are minimizing the output interference plus noise power, but because AS here, AS bar here is the presumed one, that's not necessarily the correct one. So we add an orthogonal component here, and this term E is orthogonal to this presumed desired signal steering vector, and such that we minimize this term, and then in this way we can find out what's this error term, and then as a result, this AS plus E would be the estimation of the true steering vector, and that can be used to improve the beamforming performance. So here we show an example, actually it's not for radar, but for radio astronomy, and in the presence of interference, and we use so-called adaptive angular response. Actually, this is one of the commonly used methods in radio astronomy. So we have the true image here that we used to generate the data. And then we see here, this is a mismatched AR image, and this is the worst case AR image. And this is our proposed method. So we can see by using this proposed method, we can achieve much better imaging results. Okay, so as we see, like to apply this method, we need to estimate the DOA and also the power. So in the next piece, I'm going to talk about the DOA estimation with the focus on sparse array and the sparsity-based DOA estimation. So for sparse arrays, the difference lags between sensor position will yield a large virtual array. So we can consider a uniform linear array possibly with missing elements. For example, here I have a uniform linear array with 4 sensors. And then when you calculate the delays, or say the lags, and then from here, you can get lag 0 and lag 1 between them, or lag 2 between these, and or lag 3 between them. And definitely you can reverse the direction, so you can get the lag between -3 to 3. Whereas if you look at this array, it's really similar. The only thing is I removed this sensor. So now I only have 3 sensors. And if you look at this one, we can also calculate lag 0, lag 1, and lag 2, and lag 3. So actually I can still get the same lags. So in this case, we call that these 2 arrays are co-array, or say more specifically difference co-array equivalents. And if you look at the coherence matrix, a 4-sensor array can form a 4x4 coherence matrix. And then when we remove this sensor, and when we consider this 3-sensor sparse array, now we need to remove this column and this row. However, we know that for uniform linear array, the coherence matrix has a Toeplitz and Hermitian property. That means this element will be the same as this. So we can copy this one to here and to here. And similarly, we can also copy this element to here. So in this way, we can fill in all these elements in the 4x4 matrix. And so again, from the 3 sensor sparse array, we can still reconstruct the 4x4 coherence matrix. Okay, so consider a signal model. We have Q uncorrelated signals impinging from θ1 to θq. So the received signal model we can represent as xt equal the summation of these contributions, and we can also write as a st plus nt. So this is a very standard array model. And then we calculate the coherence matrix of xt. We get rxx and equal to a rssa emission, where rss is the coherence matrix of the sources. And for uncorrelated sources, this will become a diagonal matrix. So if we vectorize Rxx, then we get vector z such that this can be represented as a tilde b and plus this sigma n square and I tilde, where the tilde a will contain columns. That's the chronic product of the original string vector and then its conjugate. And so in this way, if we look at the Z amongst a receive array of a virtual sensor, or say virtual array, and or we can call that as a difference coarray. So in this case, the manifold matrix, this A tilde actually is expanded because we are using a chronic product here, or that corresponding to the lags we talked about in the previous page. The problem is that in this case, we do not have any time snapshot anymore, so we only have a single snapshot. Okay, so now the problem is how should we design the sparse array and how should we perform DL estimation from this kind of co-array data? So actually, this sparse array and sparsely based estimation now is really popular. And if you look at the timeline, and in 1950s and 1960s, the concept of so-called minimum redundancy array was developed, and then followed by the minimum whole array in 1970s. And then a significant breakthrough was made by the Caltech group to develop systematical sparse array design represented by the nested array and the co-prime array. And that's around 2010. And so they used the music and the spatial smoothing methods. So the problem is they can only utilize the consecutive lags. And also a very significant event is in 2013, Office of Naval Research launched a program to support core prime sampling that propelled the research and development in this topic. And in 2015, we developed a generalized core prime array and also used the sparsity-based DL estimation. So in this way, we can utilize all the lags, not only the consecutive lags. And in 2019, we developed to use the array interpolation. In this way, we can fill in missing sensor positions. And then recently, we proposed the use of redundancy-free sparse arrays. So this is the minimum redundancy array, and was initially talked about in 1955 and then 1968. And then again in 2010 and 11, so the Caltech group developed the core prime array and also nested array. And so the core prime array actually used the two sub-arrays, and with here M and N are core prime. And so one sub-array used N sensors with MD spacing, whereas the other one used M sensors with ND spacing. So when you put it together, you can get the difference co-lags, like difference lags like this. And here we can see that these lags are consecutive, whereas here we have some holes. Basically, in the lag domain, they are missing. So they proposed to use the music-based DL estimation, and then because we know now for the co-array domain, we only have this Z, we only have one snapshot. So apparently ZZ Hermitian is not a full rank, so we need to perform spatial smoothing to restore a full rank concurrence matrix so we can apply music. And for these purposes, to perform spatial smoothing, we can only use the consecutive lags. So in this case, we can only use the lags between -9 to 9, whereas other lags we have to discard. So we propose to use a sparsity-based DO estimation. In this way, all the lags can be used because we do not need to perform spatial smoothing. And also in this direction, we designed two generalized co-prime arrays, and that will allow a very flexible sparse array design. And also actually that opened the door for many other sparse array design to follow. So here, the Kansas compresses the inter-element spacing of one subarray, and in this way we can achieve more consecutive lags. Whereas the Candace, we put these two subarrays in a collinear way, and we can increase the unique lags. We can also reduce the mutual coupling. And then in 2018, we developed the array interpolation technique for sparse arrays. So in this way, the missing interest in the concurrence matrix can be interpreted through matrix completion and exploiting the topless property. So for example, if we have an array of 3 sensors here, we have this position here, and another position here. So if we reconstruct concurrence matrix, we would have like this. So we only have 9 elements filled, and whereas all other elements are missing. So when we utilize the topless property of the concurrence matrix, then we can fill in these positions by just copying the values here and to here and to here. And so in this way, we fill the most of the elements in the concurrence matrix. However, we still have a few elements missing. So what we can do is we can use the matrix completion to fill in all these positions such that we can reconstruct, in this case, the 5x5 concurrence matrix. You use only 3 sensors. So mathematically, we can formulate this one into this formulation. So here we minimize the rank of the concurrence matrix. We reconstructed from this 1 column vector that we needed to optimize. And constraint that for these observed missing samples, the resulting concurrence matrix should have similar interests. And here, the rank operation is non-convex, but can be relaxed into convex nuclear norm of this. So as a result, because we obtained the full concurrence matrix, and the result will support griddless DO estimation using, for example, DOA, and it's more robust to noise, and in the case when we have a small number of samples. Okay, and recently we are discussing the optimized redundancy-free sparse array design. So in this case, because we can use the array interpolation, so really the array does not have to generate a consecutive lags, and it's more important to have redundancy-free. So in this way, we can achieve highest degrees of freedom. So by redundancy-free, we mean that all the non-zero lags would appear at most once. And again, because the array interpolation allowed hosts, so we can use this kind of approach to further add degrees of freedom and also to reduce the mutual coupling. So what we are going to do is we minimize the position of the last sensor, means the aperture, and we can specify the desired array aperture. We can also specify the minimum separation between 2 antennas. And this one involves integers in the optimization, so we have to use the mixed integer program. And for example, here we show the minimum redundancy array using 6 antennas, and the minimum whole array, and also our proposed methods. So we can see that actually the aperture, we specify the aperture of 22, and also we specify that the minimum spacing is 2D between sensors. So we do not have a significant mutual coupling, and also we get the highest degrees of freedom to compare with them. So we can achieve more sources and but also, if you look at the effect of mutual coupling, these two arrays are sensitive, whereas our proper method is really insensitive. When you have a larger array, for example, in like massive MIMO, we can also reduce the number of RF chains. Right? You are using a large number of antennas, but we can reduce the number of RF chains by compress the result. So we can put analog compress sampling matrix phi to reduce the number from the N antennas and to M RF chains. And so we can design or optimize this phi by minimizing the mutual information between the signal theta and also the compressed output Y. And so we can see that, for example, if we have 50 antennas and we reduce them into 10 alpha chains, we can still get a very robust DO estimation. For this example, we have 9 sources. And also really interestingly, because we are using the compression to focus, focus the our beam actually, or toward the toward the signals, we can achieve actually better performance when the signal to noise ratio is low, or it only requires less number of a snapshot compared with the uncompressed case. And we can also actually show that these days we are many people are interested in deep learning, and we can also show that actually deep learning is really effective to provide the robust DO estimation and channel estimation. And we considered a partially calibrated distributed array, and then by training a neural network to perform DO estimation with antenna gain and phase errors, we can achieve robust DO estimation. Whereas if we do not have this kind of capability, say conventional music would not be able to estimate the DOS in the presence of the antenna gain and the phase errors. So for the remarks of the second part, radar communication coexistence, the coexistence of different wireless systems definitely introduce mutual interference. And we consider robust beamforming to enable effective interference cancellation and the desired signal preservation. And the DO estimations was long considered as a radar task. But now apparently people in the communication community also realize that it's an important part of our communication to perform robust beamforming and also channel estimation. So sparse array designs and sparsity-based processing would provide great potentials to enhance sensing and communication capability and performance improvements with reduced complexity. And machine learning methods definitely can be trained to provide robust beamforming and DO estimation in adapt environment changes and also calibration errors. Okay, so in the third part, I'm going to talk about passive radar. So I think I don't have much time, so I will skip some of the materials. So passive radar will exploit signals of opportunity that are designed for other applications, such as broadcasting, wireless communications, and satellite navigation. So the advantages include no dedicated spectrum will be needed for radar because radar does not have to transmit anything. And you can have a low-cost implementation because you only have receivers. And you can achieve so-called multi-mode and multi-static diversity because you can collect transmit information maybe from broadcast, from satellite navigation, so you can gather different kind of signals. And also you can achieve multi-static diversity, means you can have multiple bistatic pairs. You can have silent electromagnetic operation. That's particularly attractive for military applications because you can fly the radar really close to the battlefield. The disadvantages includes the signal bandwidth is typically narrow for broadcasting and wireless communications. and the waveforms are not optimized for radar sensing. And also because the sources are third party, so the radar does not have a control, and in the worst case, the sources can be turned off and the radar cannot operate. So this one is a little old, but lists different kind of sources we can use, range from like FM and the digital audio broadcast and the TV. And apparently digital TV actually is the preferred operation for many passive radar systems. So anyway, this table gives like this kind of sources with a different frequency band and modulation scheme and bandwidth, and also the transmitter power. So a typical radar would have two parts. One part is the surveillance channel trying to get the target information, whereas the reference antenna trying to get the information of the transmitted signal, because the radar does not have the transmitted signal to perform various operations. So we mainly consider the sparsity and the group sparsity-based processing for passive radar. Because radar signals has a low bandwidth, as we just talked about. On the other hand, it has the availability of multiple sources of opportunity, and also the things are often sparse, particularly when we are interested in moving targets. And so we have demonstrated the usefulness of sparsity and group sparsity-based techniques for radar imaging and moving target tracking or localization and cloud separation. So if you're interested, we have a tutorial given in 2019 radar conference, and it's available in IEEE Explorer. And also we have a review article on this topic. So to think about, say, like a passive radar for synthetic aperture radar. For this example, we consider we have three transmitters, and then the receiver will fly over for a short angle. So in this case, in the so-called wave number domain, we can achieve three pieces because we have three bistatic pairs, each corresponding to the these transmitters, and also this region will be decided by the angle you fly over and also the signal bandwidth. So in either way, we can see that the observed wave number region observation actually is sparse and random. So if you use the conventional Fourier-based techniques, for example, back projection, actually that's the standard way to perform SAR imaging, that does not provide high quality SAR imaging because, again, of the narrow band signal bandwidth and because of the random sampling pattern, or say these positions, right? So, so basically the idea is, if you have a dense observation in the wave number domain, by doing the Fourier transform, you get a good SAR image. Whereas in our case, because we only have these three pieces here, so if you do the Fourier transform, you would get a really poor resolution and also high side lobes. So what we're trying to do is to utilize the sparsity in the scene, and then we can use the sparsity and group sparsity-based method to reconstruct the image. So we can just show one example here. We use the 3 dBm digital video broadcast signals and the 3 transmitters here, and we have a receiver here that flies for a 5-degree sector. And so because of the low resolution and the bandwidth of the signal is 7.8 megahertz, so we see that, if we use the back projection, the resolution is really poor, whereas by using the compressed sensing, we can get a very high resolution images. We also use the passive radar to perform target tracking by using Doppler only observations because of the narrow band feature. It's much more convenient to use the Doppler observation, and also Doppler observation. In this case, actually, we are using multiple receivers. So Doppler observation does not require us to update very quickly, and the information is really low. So we can achieve information fusion with a really low data traffic. And by using compressed sensing and also followed by the multi-tagged tracker, we can achieve a really good estimation performance. And we also use the passive radar to perform space-time adaptive processing, but I'm going to skip this part. Okay, to summarize the passive radar part, passive radar provides a green solution for radar sensing because it does not emit signals, and also it can be implemented with a low cost. So it's really attractive in many applications, particularly when you do not have the spectrum, and it's a convert, and also it's difficult to jam because it can be difficult to be identified, and also it will be much easier to have a dense deployment, particularly say like for example for drone detection. And at this moment, I think we see more interest from the defense and homeland security sectors, and also concerns that remain regarding the performance and also the operational guarantee, because again, the radar does not have the control of the sources. So to conclude my talk, we consider three parts, again, joint radar communications and the radar communication coexistence and the passive radar. So for the future direction, I think sensing and the communication functions will be more closely integrated. And for example, we can consider multi-function radar. For example, we can have UAV networks for both of functions, and also automated radar and V2X. And definitely, we are more focusing on the array processing. So but we can see that array processing exploiting convex and mixed integer optimization, sparsity-based processing, information theoretical learning, and machine learning would play critical roles. That's for my presentation. So I would like to the members, team members, contribute to this talk. And also thank you very much. So I listed my personal website and also my lab's website here. So if you have any, welcome to contact me. Thank you very much for your attention.
Okay, thank you very much, Professor Zhang. So very wonderful talk, and we have received a number of questions. And so since you have talked about the neural networks, I have a question from Stefan. So Stefan, can you ask Professor Zhang by yourself?
Yeah, sure. I hope the audio is a little bit better now. So my question is, you talked about using neural networks for...
Sorry, Stefan, we cannot hear you very clearly.
Okay. I'm moving closer to the microphone. I hope it comes. I have no idea what the issue is. Maybe otherwise, I hope, is it better now?
Sorry, Stefan. I think we lost your voice. Okay, maybe I can repeat his question. So he's asking, can you elaborate on how neural networks can be used for more robust DOA estimation? How are those networks trained? Is this problem modeled as a classification or regression task?
Okay, very good question. Thank you. I believe at this moment, most of the work on machine learning based DO estimation is based on kind of simulated data, I think, to train the neural network. So the idea is you can, although you don't have the real data, but you can, consider all different kind of situations and to train the neural network. So really, I think it depends on, it all depends on how you can understand the real operation environment and how can you generate the data to train the neural network. I don't know whether that answers your question or your concerns.
Yes, it does. Thank you. Because I'm always wondering, because using measurement data, which is like inherently ambiguous, right? It's very hard to train a neural network with that. So I think what we have to go for here is like a model-based approach where we use simulated data and then see how we can improve the performance of measurement.
Yes. So actually similar questions, I believe, have been discussed, and I also personally actually, listened to a few similar discussions. I mean, this is always, I believe it's not like a solve the problem, but yeah, I think that, I think that, as time goes on, probably we have better solutions. But at this moment, I would say, a very standard answer is, yeah, we're trying to basically, as much as possible, we generate data that will reflect the real operation environments.
Yes, thank you.
Thank you.
Okay, thank you, Stefan. So we have another question from Huiping Huang regarding the robust beamforming. So Huiping, can you ask Professor Zhang by yourself?
Yeah, sure, thanks. So first of all, thanks Professor Zhang for this interesting talk. And yeah, I have a detailed question regarding the reconstruction of the interference plus noise covariance matrix, which you introduced in slide number 19. So to reconstruct this covariance matrix, we need to estimate the power of the interference, the DOAs of the interference, and as well as we need to know the noise power, right?
Yeah.
And as I know, we can use the smallest eigenvalue of the sample covariance matrix as the noise power, as the estimate of the noise power. However, this estimate may not accurate enough when the SNR is low or when the number of snapshots is limited. So my question is, how can we get a better estimate of the noise power in such case?
Yeah, actually, there are quite some works in this direction. Actually, I think a better solution actually is to use compressed sensing actually to estimate or say sparsity-based processing to estimate the power of the desired signal and also the power of the noise power. Actually, yeah, we also have some papers talking about this. So I think because sparsity-based processing, you can put this. I think we can probably look at just this kind of formula, because it's minimizing the error between the observed data and also all the parameters here. So this B in this case actually includes signal power and also the noise power. So it's a parameter to be estimated, just not like in the subspace based. Yeah, you just average the minimum eigenvalues. So again, yeah, sparsity based estimation should give you better solutions.
Okay, thanks.
Thank you.
Okay, thanks, Huiping. So another question is from ISAC. So he's asking about the coprime linear array. So ISAC, can you ask the question by yourself?
Yes. Am I audible?
Yeah.
Yes.
So please, go ahead.
Okay. Yes. My question is, in coprime linear array, so we will end, still the problem of ambiguities persist, though it resolves the unambiguous estimates, but still for few set of angles, it encounter a problem of manifold ambiguity. So my question is, what is your comment on research towards resolving manifold ambiguity in coprime linear array and other sparse array?
I'm not sure. Actually, can you clarify what do you mean by ambiguity in the manifold?
Say, for example, in coprime linear arrays,
yes,
for few set of angles, what happens is our directional matrix becomes not a full rank, in the sense it violates the full rank conditions. In that case, so we will get some unambiguous estimates of DOAs, so which has to be resolved. In general coprime linear array, we will do the subarray based processings. So we will collect the data from one subarray and we will collect the data from second subarray, and we will find the DOA estimation, and wherever it gets matched, so that is what our actual DOA.
No, I think that's actually not the way. I think this concept was presented in in P and PP's original paper, but that's not really the way they or us are doing DO estimation. Actually, by pairing, the DOAs using different subarrays. Actually, in general, we put these sub-2 arrays together. So if you look at the peers work on, using music-based processing or different, there are a lot of follow-on works, or the sparsity-based processing, So this is not the way. Actually, we put these subarrays, 2 subarrays together, and so there is no ambiguity in the manifold actually, and also the match is different is a full rank.
Yes, sir. But in this configuration also, recently a paper proposed, and in this unfolded co-preliminary configuration also, we will encounter the manifold ambiguity. For few set of angles, still that directional matrix is not hitting full rank. So it is rank deficient for few set of angles.
Okay.
So because that might be the one reason, that because the interelement spacing here are greater than λ/2, which means we are not following that spatial sampling process here, in the sense not less than λ/2. Maybe that might be the one reason for some set of angles this may not met.
I mean, the idea is this, right? If you think about, from the comprehensive perspective, okay? So if you have so say for comprehensive, right, you can sample signals randomly. Okay, the idea is you cannot have equal spacing decimation. Okay, so for example, you cannot have like an equal spacing array in this case, right? If you have a array designed, say like with one wavelength apart, okay, then you would have ambiguity. Whereas if you have a random placement of the sensors, okay, then you will not have this kind of ambiguity, right? So you can reconstruct signals. So say in comprehensive, you have to sample signals randomly, and so in the array case, it's the same, right? So the antenna cannot be placed uniformly but sparsely. Okay, then you cannot reconstruct. If you place them sparsely but not uniformly, then there will not be ambiguity. Okay, there could be high side lobes, but you cannot say there are ambiguities. Okay, because what's a grating problem? Because if you have a grating problem, apparently this problem cannot be solved. But the array is designed to not have this kind of problem.
Okay. Thank you so much.
Okay. Thank you.
Okay, thank you. So I think we have a final question from Longwei Tian. So he's asking about, again, I think robust beamforming. So Longwei, please, can you ask by yourself?
Oh, yeah, sure. Thank you very much.
Thank you.
I would like to ask 2 simple questions. And my question are mainly about the assumption of signal correlation. And my first question are on the page 18. Does the equation on page 18 have the underlying assumption that the signals are uncorrelated, or we can say equivalently the coherent components in the covariance metric is omitted?
I'm sorry. I think probably you're referring to different slides.
Yes. On this slide.
Okay.
My question is that does this equation here has the underlying assumption that the signals are uncorrelated?
So you mean you want to talk about the signal correlation between desired signal and interference, right?
Yes.
I cannot say differently, but I believe this one works because this one's canceling the, once you estimate them, right? This one trying to cancel the signal from the interference plus basically canceling the signal from the interference directions. So yeah, this one should work. The problem probably would be how do you estimate the this signal directions and steering vector in the presence of correlated signals, right? So that's the problem of the DU estimation and power estimation. But I think once you reconstruct this coherence matrix, I think you should be fine.
Okay, and my question is focused on because they are k components in this equation, yeah, and my question is that there has the possibility that such k signals they may have the coherent component here, and in that condition, this matrix, this covariance matrix may have an extra component here.
I think what you're talking about is if you calculate the covariance matrix between coherent or correlated signals, they would have more terms. So, but this is a different approach, right? This one basically says, I estimate the DOA and the power of each components, and then I reconstruct this way. So basically it will, mitigate the directions, mitigate the components in these directions. So I think these are kind of like a different, either say approach or a different formulation, I think.
Okay, thank you.
Okay, thank you.
And my second question is on the page 23, and 23, yeah, and here they have the same. Here has assumption that the signals are uncorrelated here, and my question is that if the assumption here is changed to signals they have a correlation, will it affect the subsequent DOA detection method or the performance?
Yeah, actually, yeah, very good question. So actually, sparsity-based DOA estimation, to my knowledge, actually mainly consider or say assume the signals are uncorrelated. And there's some work also considering the case with coherent signal, but I think there are very few papers or publications talking about cases with partially correlated cases. I think that's really challenging, and this kind of model actually does not apply. So this is still kind of like an open problem.
Okay, thank you very much.
Thank you.
Okay, so thank you very much, Professor Zhang. I think that will be all for today's talk, and thanks again for accepting our invitation to give this very wonderful talk.
Okay, thank you again for invitation and also for everyone to attend. Thank you.
Okay, thank you. So we hope to see you in your future events. And yes, so I think that'll be all for today. And we will announce our next event in which will be happening in January, because we will rest for the December for the Christmas. So our next webinar series will be at January. So we will announce the details very soon, and stay tuned. Okay, thank you guys. Thank you for listening, and goodbye.